Yeah, let's get back to where we were. So here now, what is this equation telling us? What is this equation telling us? What is this equation telling us? You guys. This red equation telling us. You have D1, right? You have D1 here, you have D2 here, right? So if they are equal to this surface charge, right? What does it mean? What is happening here? What will happen to the fields if this is not equal to 0, if this is equal to some surface charge? I mean, just an idea. I'm not saying, just an idea. Exploring ideas. What will happen? Okay, let me make it more simple. What will happen to electric field? Will it be affected or no? If there is a surface charge, right? If there is no surface charge, this will be equal to 0. If there is a surface charge, well, of course, this equation is equal to this. So actually, what is happening here? What will happen to the field? Will the field change? Yes. Yeah, good. The field will change abruptly. Yes, the field will change. Yeah, good. Yes, the field will change. If this is the equation, right, the field will change abruptly. Field will change. Yes. Thank you. Now, second condition. If the surface charge becomes 0, if this equation is equal to 0, of course it is opposite to this, right? This will pass freely, there is nothing. Smoothly, right? Smoothly it will pass. Smoothly it will pass. If that they are equal to 0, will pass smoothly. No change, no abrupt change or nothing. It will pass very, very smoothly. That's what. And for B, this is for electric. What for magnetic? Why it's not equal to rho s? Why it's not equal like this? Straight away it's 0. For magnetic, right? Unlike this, for electric, in magnetics, they are always equal to 0. Always equal to 0. The reason is, and it's very simple, a very simple answer to this. Why? Always, all the time, it will be equal to 0. All the time. It is close. Just give me a very simple reason. Very simple reason. See, see this equation means they are continuous, right? Continuous. Then, what is that very simple reason? It is a? What do you mean by close line? Okay. Does magnetic charge exist? Do magnetic charges exist? Do monopoles exist?
I'm talking about magnetics. Do they exist? No? So that's why. Why zero? Right? That's why. It's a very simple, right? We know that in magnetism, there is no magnetic charges. If there is no magnetic charges, of course, that's zero. This is the explanation for this. The normal, this is not the explanation. The normal components of the magnetic flux intensity are always continuous at the interface. Well, that's why they are zero, right? Yeah. But again, there are no magnetic charges, right? That's why it's zero. That's the explanation. Now here, this is the tensile component of E, right? You have a medium 1, you have a medium 2. Their properties are different. Of course, their properties are different. Here, there is this enclosed path, this kind of rectangle A, B, C, and D. Right? Here, why this is equal to 0? This is equal to 0. Right? Here, this equation pointing to this way, it is equal to 0. It's a basic definition of line integral, right? Basic definition of a line integral of the electric field. It's a closed path. Both are opposing each other. It is 0, right? So here, if somehow this delta H, which is this, right? If it goes to 0, what is happening? Well, it is equal to 0, right? It is equal to 0. So we can write that in this form. So here, again, here, that is equal to 0, which means what? The tangential component of the electric field intensity are always continuous at the interface. At the interface, right, at the boundary, the tangential components of the electric field intensity are always continuous at the interface. What does it mean they are continuous? Why? Okay, it is 0, fine. They are continuous, but further, let's explain it further. The tangential component, right? What are tangential components? Here are tangential components. These are tangential. You can, from this figure, you can tell, right? These are tangential components moving along the surface, right? Moving along the surface. And then here, when we say, and keep that in mind. Keep that in mind. Those tangential components, right? They are not changing. So when we come here, we say, okay, here we say the tangential components of the electric field intensity are always continuous at the interface. We just saw that, right? Meaning what? Meaning what? If they are continuous, then what? Right? That comes, the question comes, what? If they are continuous, then what? What if there is some value like, let's say I put JS here. Then what? Let's say I put JS here. Then what? And let's say I don't put it, I equate it to 0. What? What is happening? this equation, this is the explanation for this equation. We say, well, the tangential components of electric field intensity are always continuous at the interface. Well, you can look at this figure, right? Look at this figure. Tangential components are moving along the surface, no change, they are continuous, right? When there is no change, that means they are continuous. Means what? If they are continuous, then what does that mean? They are continuous. How can I explain that? Right? Yeah. Always continuous at the interface. We just saw it. They are always. Then what does it mean? They are continuous. That means they. Okay. Are they changing their value? No. They are not changing the value, right? That's what continuous means, right? They are not changing the value. They are not changing their value, right? They are moving along from one surface to another. They are moving along. So, sorry, on surface they are moving from one medium to another without changing. Look at the figure again. Here, the tangential components. Here, they are moving along. They are continuous. They are not changing value. That is what it means. Continuous means they are not changing. Moving from one medium to another medium, they are not changing, right? They are not changing the value. That is what it means. Okay. Now, what about H? What is happening to H? Why it is equal? Why it's equal? Why it's not equal to 0? Electric is 0. Magnetic is chaos. Right? Surface current density, right? The current density. Why it's equal to current density? When we talk about H, when we talk about E's electric, we say it is equal to 0. They are continuous. What about H? Surface current, it is equal to surface current density. And H is medium 1, H2 is medium 2, right? It is equal to Js, which is the current surface current density. Is there any mistake in this? Okay, first let's talk about how would I explain that, right? I already explained that if it's equal to 0, I'm talking about the electric field. If they are equal to 0, that means if they are moving from one medium to another medium, it's continuous. Nothing is happening smoothly. The waveform it is moving along smoothly. Nothing is happening. Fine. But when we talk about the magnetism, right? We say it is equal to Js, and Js is what? Current density, right? So yeah. So what is happening then? If there is yeah. So how would I explain this equation? We explain that equation. How would we explain this equation? It is equal to Js. It's not equal to 0. Js is current density. That means, okay, let me simplify. If there is a current, what is happening? If there is a current on the surface, if there is a current, if there is a surface current, right, what will happen? Will it be continuous or no? Will there be a jump? If there is a current on surface, it's called surface current, right? If there is surface current, then I have changed my equation for that mean? Oh, okay, what will happen to the field if there is a surface current, right? This is density, current density, right? Does that mean there is a current present on surface current, right? Will it be continuous or will it be discontinuous? It will be discontinuous, right? So there will be a jump. There will be a jump. So that is what it means, right? There will be a jump. Due to that surface current present, there will be a jump. That's why we don't equate it to zero. We equate it to change, which is the current density, or surface current density. Because there is a current on surface, there will be a jump in the field, right? There will be a jump in the field. Of course, right? Current will affect that. These are the fields at dielectric interface, fields at the interface with a perfect conductor. These are called perfect conductors, and these are the magnetic wall boundary conditions. These are few conditions. The magnetic wall boundary condition is analogous to the relations between the voltage and the current at the end of an open circuit transmission. Right? The magnetic wall boundary condition is it's equivalent. Look like the relation between the voltage and the current at the end of an open circuit transmission line. Open circuit, right? Nothing open circuit. And while the electric wall boundary condition is equivalent to the voltage and current at the end of a short circuit transmission line. So you could relate those, right? These three lines are important relating to the electric wall. So the magnetic wall boundary, right? The magnetic wall boundary condition, those ones, they are equivalent to the relationship between voltage and current at the end of an open circuit, while the electric wall, the above one, it is equivalent to the short circuit transmission line. Short circuit transmission line. Here, if you notice this one, here the transitional field is equal to 0, right? You could see, you could read further. The wave equation and basic plane wave solution. For a uniform but source-free medium, this is the Maxwell's equation, right? Ampere's law, Faraday's law, right? Take the curl of Faraday's law, right? If you take the curl of that law, what you get? You get this, right? You get this? You are simplifying. You are going along. The final equation, this one here, this is called the Helmholtz equation. Helmholtz equation. Right? If you take the curl of this Faraday's law, you keep on, simplifying it or keep on putting different terms, you will end up at this is called wave equation or the Helmholtz equation. Helmholtz equation. These equations are related to what? Related to what? Like there is a question, right? Okay, I'm taking the curl of the Faraday's law. I'm trying to simplify the equation. I plug in some blah blah blah. Finally, I got this equation. Well, we call it wave equation. Then what? Then what? What? Right? And source-free medium. Then what? They are how the field propagates through the medium, right? They are related to how the waves move, how the fields move through the space, how the fields move through the space. That's what they are meant for. Plane wave in a lossless medium. Lossless medium means, well, there is actually no lossless medium here, but let's say ideal condition. Ideal condition. So we are applying those equations, right? Wave equation or Helmholtz equation. The component of the field quantities E and H lie in a transverse plane, the plane perpendicular to the direction of the propagation wave. We refer to such wave as plane wave. We refer to such wave as plane wave. The plane wave moves in the z direction. The plane wave moves in the z direction. So the transverse electromagnetic wave, for that, E of z is equal to 0 and H of z is equal to 0. So the transverse component Ex are like this. Right? This is a transverse, a uniform plane wave. For those, a field has the same magnitude and direction in a plane containing it. So this are zeros. Here, okay, here it is the plane wave propagate in the z direction, right? And here, if we plug on those values, right, in that plane wave equation, this one, the propagation constant, this k, which is equal to this, right? K, it's called propagation constant. Now, okay. So here, what does it mean if they are equal to 0? They are equal to 0. When you put those equal to 0, what does it mean? When you put all those terms, 1, 2, 3, 4, 5, that curve or partial fraction of t by the t, you are putting equal to 0. So what does it mean? Direction. They are same. Same means what? There is no component, right? Those components are 0, that means there is no component. There are no components in those directions, right? There are no components in those directions. So now, they have defined this quantity, this omega mu as epsilon, propagation constant. Propagation constant. So what does it mean, propagation constant? The wave's amplitude and phase. What is the definition of propagation constant, right? The waveform, the wave amplitude and phase changes, right? This is called propagation constant, right? What is a propagation constant? The waveform or the wave, the amplitude and phase changes when it is passing through a medium, right? It changes. The phase and the magnitude changes. This is called propagation constant, right? Agree? Agree? propagation constant basically is how the wave changes its magnitude and the phase when it passes through a medium. That is propagation constant. So here, if you look, this waveform in the time domain, it is moving in the positive z direction and it is moving in the negative z direction, right? Moving in the positive and the negative z direction. And then the next term is called the phase speed. The phase speed here, the speed of a plane of a constant phase. Phase speed, called phase speed. So this is the phase speed. How you define phase speed? Here, if you take the derivative of z with respect to t, so you will get what is called the phase speed. For space, phase speed for a dielectric is this, right? You know what a speed is, right? The wavelength, the distance between two planes, when the phase difference between them at any given time is 2 pi, right? 2 pi. So this is basically lambda. What is K? K. Yeah, what is K? Oh, K is coming from there. Omega t minus K is coming from there. This is for the magnetic field, we have this, right? Plane in a lossless medium. A plane wave traveling, this is for the H, right? This is called intrinsic impedance. Now, new term, intrinsic impedance. That is, how would you define intrinsic impedance? The ratio of intrinsic impedance. Yeah, if I want to relate this intrinsic impedance with electric and magnetic, you can see in this equation, right? You can see in this equation for intrinsic impedance, that is mu, that is equal to mu, that is equal to mu divided by epsilon. How would you define that? It is what? It is the ratio of what? Ratio of electric to the magnetic field, right? Ratio of electric to the magnetic field, right? Example, a plane wave propagating in a lossless dielectric medium has an electric field given as this, with a frequency of 5 gigahertz and a wavelength in the material of 3 centimeters. Determine the propagation constant, the phase velocity, the relative permittivity of the medium, and the wave impedance. Okay, do it. Solve. And who will give me the answer? You have access to those slides, right? Everyone has access to slides? No? Oh, you will bring your... Okay, so, yeah, so let's do it then here. I thought you would have your, handheld devices, you could solve it. Okay, so, here, right, simple, just need to plug in the values, right? Just plug in the values. You need to find what? You need to find the propagation constant, the phase velocity, the relative permittivity, and the wave impedance. Well, in the previous slide, we have all those formulas, right? So just plug in here. So here are phase, relative permittivity, wave impedance, right? This is the wave impedance. Simple. Now we talked about lossless material. Now let's talk about the lossy material, right? So what about that? Now, lossy material. Here, same thing we are doing, right? Now there is this new term. Right? Here we have this new term. Let's call it gamma. It's now it's a complex, right? Now it's complex. Why it's complex now? My question. Why all of a sudden this propagation constant becomes complex? Why? Before, in a lossless, because yes, because it's a lossy material now, right? We are talking about a lossy medium, which means there is a loss, right? Loss of an element. So that's why, and we need to reflect that loss, right? Who will reflect? The J, right? The second component will reflect that. That's why we have this complex propagation constant now, right? Because it's a lossy material. Right? So this is basically reflecting loss of energy, or loss, whatever you call it, loss component. Now here it is defined as in terms of alpha plus j beta, right? What is alpha? Alpha is called the attenuation constant. Alpha is attenuation constant, and it's real, right? What is beta? It's the phase constant. Beta is the phase constant. Okay, it's a constant. Both are constant. What do you think the unit of both will be? The units. Alpha. Okay, let's start with the phase. The phase. What would be the unit of phase here? What's the unit of phase? General. Huh? Radian, right? Radians per meter, right? Radians. What about alpha? Alpha. What? Per? Nepers per minute, per meter, right? Nepers. Yeah, Naper. NP per M. NP divided by M. Nepers per meter, right? Nepers per meter, yeah. Okay. This represents a wave traveling in the positive direction with a spaceship velocity of that and a wavelength and an exponential damping factor alpha. Exponential damping factor this. Plane wave in a general, what happened to the, okay. Now the magnetic field, here is the magnetic field. The intrinsic impedance of the conducting material medium is now this, right? So it is what? It is the ratio of the electric to, we already talked about that, right? Ratio of the electric magnet and magnetic field components. What about the plane wave in a good conductor? Plane wave in a good conductor or a high loss material, this is the condition for that. Either the conductivity of the medium is very high or the wave frequency is very low, right? Either the conductivity of the medium is very high or the wave frequency is low. Which of the material will have a high conductivity? We talked about, let's say, real scenario, real world scenario. So far we are talking about materials. We didn't name any material. Let's say we want to name a material. We want to apply this condition. The conductivity, we are going to apply this condition, right? Which material comes to your mind? Simple. In this building as well, you can see. So either the conductivity would be high or the frequency would be low, right? Either the conductivity high or the frequency is low. Both ways. Either the conductivity is high or the frequency is low, right? So which material comes to your mind? Either the conductivity is very high or according to this condition, this omega, it should be, right? So what comes to your mind? A material. Copper, right? Copper. Copper conductivity is very high, right? Copper, right? Copper is a very high conductive material. So what will happen? If I have a copper, right? Here, this is conductivity, right? This is conductivity. We say, well, either the conductivity has to be very high, right? Or the frequency should be very low, according to this condition, right? We say, we identify a material, it's a copper. What will happen? Copper. Wave. Right? If the material identifies copper, so the wave will be having very hard time to penetrate. It will die down after some time, right? It will die down. It's not easy to penetrate. The wave form, that wave will die, right? It will lose all of its energy, right? It will lose all of its energy, which means it will be attenuated. It will be attenuated, right? If it's attenuated, we call that skin depth. That is coming after the slide. Skin depth. What is skin depth? Okay, let me go to this slide. See here, the skin depth. Right? What is skin depth? Like material like copper, which has a high conductivity. The wave, it is very hard for the wave to penetrate. It will be attenuated quickly, shortly. It will be attenuated, right? That process or that thing is called skin depth. Okay, it is called skin depth. How you define that skin depth? You define this thing. This is skin depth, right? So what is skin depth? How much distance did it cover how much distance this wave covered before it dies down, right? It is called skin depth. Skin depth, right? How much travel or how much distance it covered before it dies down. It is called the skin depth. And this is how you represent skin depth, right? This is the formula for the skin depth. Now, how can I explain this equation, right? Omega change into, 2 pi, right? 2 pi f. What is happening here? What is happening? Skin depth is, okay, this is skin depth, right? This is equal to 1 over f pi mu and this sigma, right? Root. What is happening? What is happening? Okay, if the frequency increases, what is happening to skin depth? If the frequency is increasing, the skin depth is decreasing, right? They are inversely proportional, right? So that means one thing from this equation, I can say that skin depth is dependent on frequency, right? Skin depth is dependent on frequency. From this relationship, I can tell that skin depth is dependent on frequency. More the frequency, less the skin depth. Less the frequency, higher the skin depth. For copper, we just discussed copper, right? For copper, the skin depth for a 1 megahertz frequency is 0.07 mm for copper, right? This is what the copper. So the skin depth for copper at 1 megahertz is 0.07 millimeter. Copper is a good conductor, right? And further, these are, well, okay. This is the comparison. Whatever we have done so far, this is the comparison. I'm just looking at the time. So we'll stop here at this slide, and then after that, your teacher, Professor Wong, will take over from here. I'll inform him. That we finish up till this slide. There is no slide number, but anyway, we'll see. You can also inform him that we'll start. Well, we finish this slide after that slide. So this is the comparison for lossless, for general lossy, and for a good conductor. This is what we have done so far, right? This is what we have done so far. Like we have discussed all those three cases. So these are different quantities like lambda, like skin depth, impedance, right? Attenuation constant, phase constant, complex propagation constant. We already discussed those all, right? This is a table which is comparing all those three materials which we have done so far, right? So I think we should start here. This is too complicated, right? Oh, there you go. Thank you very much, everyone.